Okay, so let's get started. So let's do a review of what we covered last time. So from last time, basically what we had is we had the practical transformer model. So what this model is basically an ideal transformer. So we have an ideal transformer. And then what we do is first we reflect the impedance from secondary to the primary side. So what we have is we reflect this, then we have some shunt elements. Then we have the primary side resistance and reactance. Okay, so this is our practical transformer model. And this, you can think of this as the full model of the transformer. So we have not made any assumptions at this point. We have not made any simplifications at this point. Then there are several simplifications we can make to this full transformer model. Right. The first is to get rid of the core elements. So the first simplification we can make is to assume that the core is to ignore the core, basically the shunt element. And the reason we can ignore this is mu c, so the core permeability is large. Okay? So it's not infinite, right? So it's not a perfect conductor. It's not doesn't have infinite permeability, but it is pretty large. Okay? So the first simplification we can make is to ignore this. And then if we ignore it, all we have left over is basically a simple circuit in series. Okay? And what we have is we have x1, r1, jx2 prime, r2 prime, where x2 prime is n1 over n2 squared, x2, r2 prime is n1 over n2 squared, r2. So this is the first simplification we can make, right? And this basically assumes that the permeability of the core is infinite. And so what's left over is this x and r terms. These come from the fact that we have a wire that's one dielectric inductor. So we can make these as so we have these sort of series elements left over. And then sometimes, for simplicity, we'll make the assumption that right, so yeah, so this is often the assumption we make, but then sometimes we assume R1 and R2 are 0. Okay? So we can assume the wire is, again, a pretty good conductor, right? So we'll assume this thing, then all we have is basically we have an inductor left over in series. So our transformer becomes an ideal transformer where all we have is some inductor. And this inductor is just the summing up the inductance from x1, x2 prime. Okay, so that's what we have. If we want a really simple model and all we have is, then we just have an inductor in series in the circuit. Okay, so normally we cannot get rid of this inductor. Okay, so even though the fact of so the resistance comes from the fact that the wire is not perfect. You lose some heat, you push current through the wire. The inductor comes from the fact that we're winding the wire this way. So even if the wire is a perfect wire, it still looks somewhat like inductor. And for a big transformer, you have a lot of windings on both sides. Okay, so it's not a small number of windings we have. So this inductance is normally there. Okay, so for a practical model, if we really want, we'll just have X equivalent. But normally we don't assume this away. Okay, there'll be some induction in series with it. Right? So any question about the transformer model? Okay, so again, in classes, so in the homework and in the exam, you'll be told which one to use. Okay, you'll be told which one to use. For example, one way you can be told which one to use is the next example we'll see. Okay, so let's do an example of looking at how do you know which of these assumptions to make, right? Do you use a full model with everything in it, or do you use a simplified model? So let's look at this example. So this example says, let's say we have a single phase transformer, and gives us the primary turn. So this is N1, N2, the winding resistance, the leakage impedance, and infinite permeability. And such impedance includes the secondary impedance referred to the primary. And then says, okay, now we collect this transformer. So we have a transformer. In the primary side, we connect this to 100,000 volts. Then we connect this to a 5 ohm load. Let's find the power supply to the load. And then our first, so if we know the model, then the circuit is not very difficult to solve. So from this example, which model should we use? What is the model that we should be using? Should we use a full model with all the series impedance and the core shunt? Or which one of these elements, right? So we have all these models. This is a full model. Which one of these elements can we ignore in the example we show?
So you look at the permeability tells us we can ignore the shunt elements.
Right. So what this says is I have infinite permeability, right? So this says you see as infinity. What this says, then this basically says the core is perfect, right? So the material of the core is ideal. So what this tells us is we can ignore the shunt. Right? Ignore the shunt elements. Okay, any questions about this? Right. So the question will always tell you, right? It may not be so explicit, saying ignore the shunt element or ignore R1 or things like this. Okay, but if you read the question, it will tell you which model to use. And one example of telling you to ignore the shunt element is to say there's infinite permeability. Okay. Or the question may say mu c is infinity, or this kind of statements. Okay, so when you look at transformer question, always read the question. Right? The question will tell you which model to use. For example, question tells us this. Then our model is the following, right? So we don't forget about the shunt stuff. So what we have is we have a transformer and we attach a 5 ohm load to this side. The question tells us what the parameter to use for the resistance and the leakage impedance. So this is 0.2. This is J.6. Okay, so these are told in question. We put 1,000 volt. This way, we want to know the power we deliver to the load. So how do we solve this question now? Okay, so this is our transformer model, right? And how do I find the load delivered to the, how do I find the power delivered to the load? Okay, so this, right, so the chat, so the Ethan says in the chat is, for all this type of question, the first you do is reflect the load from secondary to the primary. You basically want to do this reflection. After doing this reflection, what we have we refer the, so this reflector will refer the load from secondary to the primary. After we do this, then what we have is we have a simple circuit to solve. Okay, so we don't have to worry about this transformer anymore. So to do this, okay, so what we do is we want to draw this circuit. So let's call this load. So I refer this load to the primary. Now, what's the value of the load referred to the primary? So I attach a 5 ohm load to the secondary. I have to refer it to the primary side. What equation do we use?
R2 prime equals to the N1 over N2 squared times R2.
Right, so the equation we use is this is N1 over N2 squared times the load, right? So this is the equation you want to remember. And that's the reason why the question tells us the N1, N2 values. So this is 1000 over 500 squared times 5, 20 ohms. 4 times 5, 20 ohms. And now we have a pretty simple circuit, right? Okay, so now the circuit is pretty simple. We have a source of 1000 volts, connect to a bunch of things in series, right? So what we can do is, for example, now we can find the current going through this. So for finding the current, these are complex impedances, but we can always assume that the source has angle 0. So this is 1000 angle 0 over the total resistance is 20 plus 0.2, right? This is all the elements are in series now. Plus J.6. This is our current. You do this calculation, we get 49.48, angle minus 1.7 degrees. So this is our current going through the load. Then this is a resistor. So what it does is dissipates active power. So what we have is the power delivered to the load is I squared times R times R times 20. You square this, square the magnitude squared times 20. What we get is 48.9 kilowatts. Okay, so this is the power we deliver to the load. Okay, so the nice thing about the power calculation is once you refer it to the primary, you don't have to refer it back to the secondary again, because power is conserved on both sides of the transformer. Right? So delivering this 48.9 kilowatts to the load referred to the primary side, this is exactly the same as power delivered to the load attached to the secondary. Okay, power is conserved. So that's why it allows us to refer everything to the primary and do this sort of circuit calculation. Okay, any questions about this example? This is very typical of a problem you'll see in the homework. This is a very typical problem. Okay, so the key thing to remember is read the question to figure out which model it is, right? To figure out which model we should use. Then refer things to the primary side to get a circuit that we can do calculation with. Then find the quantity we want to find. All right, so this wraps up the first part of the transformer section. Then we'll go to the next part of the class, which is the per unit system. Okay, so per unit system, this is chapter 3.3. So if you read the book, it's in the same chapter as transformers. And the reason is this per unit system is mostly created to deal with transformers. Because if you look at this transformer, right? So how did we do this question? We said there's a transformer, we have a load attached to it. So let's keep referring it to the primary side. This works if we have one transformer in the system, okay? And we have a primary and secondary side. But in the actual power system, we don't have this. What we have is, so in the actual system, what we have is more like the following. I have a generator, this goes some transformer, I have a transmission line, this goes through some transformer. Let's keep going through transformers, a chain of it until it gets to a load. So until it gets to some load. Okay, so this is really a chain of transformers. And if it's really just a long chain like this, fine, you can refer things, you can keep refer things. But what happens is you have branch connections, going through different number of transformers. The transformers may not have the power rating or things like this. Okay? Then if in every calculation, what we have to do is to take a load, keep referring it to the primary, and do a lot of this sort of reflection things to get the circuit correct. There's a lot of work for us. So per unit system says, let's have a systematic way of doing this. Okay, let's have a more systematic way of hiding the sort of transformers, right? And so we can write down equations and not worry about transformers so much. Okay, so that's why per unit was discovered. And per unit also deals with the following, right? So, and the more higher level deals with the following fact: is units in the power system really is all over the place. It really is all over the place, right? So we have generation. When we talk about generation in a large system, we talk about gigawatts or hundreds of megawatts. We talk about voltages, we talk about hundreds of kilovolts. We talk about loads, we talk about ohms. Okay, we talk about ohms. Remember the last example we did? We consume about 50 kilowatt of power, but our load is 5 ohm. Okay? So you have numbers that's orders of magnitude different from each other. Going from if you talk about line resistance as fraction of ohm, and you connect to a generator that's generating a few gigawatts. So we have this sort of numbers across a very large scale. That's normally not very easy to talk about. Okay? We have units that's sort of too far away from each other, right? And so we have a big dynamic range. Okay? That's not easy to talk about. It's actually not also easy to do calculations with, because then you have to store a lot of floating numbers that goes from very small to very big. And if you're dividing and multiplying with all those sort of very numbers on very different scale, it's easy to make a mistake and rounding become an issue. Okay? So, and as we said, the transformers, when we talk about transformers, we have every time we have to specify referring which part to which part. Okay? So a lot of difficulty if you want to analyze the system in this so-called SI units, right? So these are SI units. And turns out they're not created to be very user-friendly to power system engineering. Right? And it's much better if all the numbers are around 1. Okay, so in engineering, we always like numbers to be around 1. Because they're all on the same magnitude, makes computation easier. Multiplying numbers, around 1 is pretty easy. And then again, multiplying thinking about them pretty easy. Okay, so when we think about a typical number, we want to think of this, this number is normally around 1. So I'm observing something that's 5% away from the nominal value. These are how we think about. We don't think about numbers, having a very big unit, right? So, okay, so we want basically per unit system as just a normalization scheme. Okay, just how we normalize things. We have a bunch of different voltage values, bunch of generation values, bunch of impedance values. How do I normalize them so the numbers are all in a reasonable magnitude? They're not too big or too small. Okay. Any questions for this? Okay, so this is for unit system. And so this will basically step through of how do we deal for unit systems, right? How do we deal with voltage, current, impedance, power, what happens when we have transformers and this kind of idea. And at the end of the day, basically, always boils down to the system looks like a simple circuit. Okay? So all the work is to get it to look like a simple circuit. So as a reminder, the first part of the class is to how to get a complicated power system look like a circuit. Second part of the class is how do I solve this? Okay? So we're still in the first part. And the idea of this liberalization scheme is pretty simple, right? Ask what you would think it is I have some actual quantity. Okay? So this is some, the actual number, my measure number. I want to divide it over a base value to get a per unit quantity that's unitless and easy to talk about. So for example, my nominal voltage at a node can be 132 kV. Okay, so I measure this 132 kV. Sorry, this is my nominal voltage. So you can think of this as a base value. Okay. So it says if things are not operating nominally, this is the value of the voltage. And I go measure the voltage, it's a little bit different, 127 kV. So we want to talk about this in a unitless, okay, in a unitless setting. So what we can do is we can say the per unit value is the actual value divided by the nominal value I have, or the base value I have. This is 0.96. So since we're dividing voltage by voltage, volt by volt, there is no, this is unitless quantity, right? But to denote, we get this from a per unit quantity, so we write this as per unit, or more often 0.96 PU. Or many times you see when you read something, we'll say we assume all quantities are per unit. So we don't even bother writing this PU. And again, this is nice because you read a number like 0.96, then we know, it's actually not too far away from the nominal value, we're probably fine. But if you just saw the absolute magnitude of 127 kV, and somebody asks you, is it normal or not normal, it's harder to answer. Right? So it's easier to do things in a per unit system. So this is for voltage, and all the others are similar. Okay, so if you talk about per unit quantities, it's basically take the actual value, divide by the base value, okay? Divide by the base value, and then figure out what the per unit value is. So any question about this conceptual idea of per unit? It gets somewhat, gets a little bit tedious. We have a lot of things to talk about, but the conceptual idea is simple. Okay, take an actual value, divide by what nominally all these values are, get a unitless quantity that's for reasonable numbers. Any question about this? Okay, so if you look at all these divisions, so these are mostly, so all this can be complex numbers, right? Voltage, current, power, impedance, these are all complex numbers, has a magnitude and a phase. So when we do per unit quantity, is it on the magnitude or on the phase or on both? What do you think the normalization should be? Right, so in the chat, that's magnitude, which is correct, right? So when we talk about per unit, it's normalization is just to the magnitude, okay? Just to the magnitude. We don't normalize angle, okay? We don't normalize angle. Because one angle is actually a unitless quantity already. Okay, so it's it's degree or radian, which actually doesn't have a unit associated with it. And also angles, the values are not too bad. It's from 0 to 2 pi, or 0 to 360. So it's not, though we don't have something that spans through 10 orders of magnitude, unlike in the magnitude case. Okay, so we don't normalize angle. Angle is what it is. We just divide by the magnitude. Okay, so for angles, there's not a notion of per unit angle, right? Just per unit magnitude. Angle is measured from 0 to 2 pi. And a lot of the thing we'll cover next is basically how do you choose the base units, right? So if you look at the equations, we need to choose this base units. We need to choose all the base units. Once we make this choice, we'll divide everything else in the system by the base units. So, the question is, how do I choose the base units, right? Do I have freedom to choose base units whatever I want, or there should be some consistency with the base units, right? So just intuitively thinking, if you look at this equation, right? So if I choose, for example, the base unit for voltage arbitrarily, if I choose a base unit for current arbitrarily, that means normally I cannot choose a base unit for impedance arbitrarily. Okay, so I should not be able to make arbitrary choice for all the base units. Right? There are some consistencies. They should also obey Ohm's law. Right? Things, ideas like this. Okay, so there's a systematic way of doing this. How do we choose base units? So if you look at the base unit choice as, right, so again, the choice should not be arbitrary. We know V equals to I times current times impedance. So we should choose the base units in a consistent manner. Right? It makes in consistent manner. We have Ohm's law. So what we should choose such a way that the base voltage is equal to the base. Okay, so this is what we want to do, right? So just to be consistent. So what we have is, okay, so what we want is we want this equation to hold, and this will imply Ohm's law still holds for the per unit quantities. Right? So base unit should not be chosen arbitrarily because we want the base units to make sense, so we can still apply all the physical laws that we know. So the problem is, so if you don't choose the base units like this, so if you don't obey this equation, then you don't have Ohm's law anymore. Okay, you have weird coefficients that are coming out in front of Ohm's law. So normally to make your life simple, choose base unit that's consistent, that makes sense. All right, so let's do it for power, right? So base power, we have the same idea, right? So we have the apparent power is V times I star. So when we choose a base unit, right? We choose a base unit. Since we just talked about magnitude, so we have V base I base. So if we choose it this way, together, what they'll give us is a per unit power. Makes sense. This is VI star over the base units for voltage and current. So the expected loss still hold. So if you choose, for example, the base voltage is 100 kilovolts and the base current is 10 amps, then the base power should be 1 megawatt. Sorry, 1 MVA. Okay, so that's the idea. It should all be consistent with choices. Then if you talk about active power and reactive power, so this is, you divide them by the same base power, okay, by the base power. And what we have as a per unit thing is as we per unit. Okay. So one thing to note about power is that there is not a notion of base active power and base reactive power. Okay, that's generally not a notion like this. What we have as we have a apparent power base. Okay, we have a apparent power base. So for example, in unit of voltage amp, then you divide that to get both the per unit for active power and reactive power. Okay, so that's how we choose power, right? And then we have base impedance. So all this is exactly the same idea. You pick a base, and then here is for the real and the reactive part, for the real and imaginary part, we'll divide by the same base, quantity. All right, so and this the per unit is just R per unit plus JX per unit. All right, and we talk about admittance as simply 1 over the base for the impedance. Okay, so this is what we have for base impedance. So, and for base power and voltage and current. So this is, so all these equations are fairly simple, right? Once you make a choice, you can divide this, you can, divide everything to get this. And really the thing that we have to think a little bit about is how to do the following. Okay, how to do the following. Suppose I have a system like this, okay? So let's say I have a transformer sitting here. I have a primary and a secondary. Okay. So there are 2 voltage level now. Right? There's 2 voltage level in this transformer. I have a V1, V2. There's 2 currents, I1, I2, okay? And the power on both sides. So how do we make a choice here then? Okay, so let's say I have a transformer. Which one should I choose, right? So I cannot choose all the units arbitrarily, right? They have to obey some of these consistency laws. So for this kind of system with a transformer inside it, how should I choose a base unit? Should I choose the current and voltage base, then compute everything else? For example, compute the base power from the voltage and current base. Should I choose the base power and compute the voltage and current base that way? How do I handle the fact that I have a transformer here? Okay, so any suggestion? How do I choose base units? Right, so first of all, let's think about, should I choose the voltage base? Should I choose a base that has voltage and current? Or should I choose a base that involves power? Those are the choices we can make. Right? So remember, in all these equations, basically we said is we have a voltage and current base unit. And we can compute everything else. But is that what we want to do when we have a system with a transformer? Do we want to choose a base unit that has both voltage and power? Or should we choose something else as a base unit first? So there's some engineering thinking here. So let's think about, if I choose a voltage and current as base units for this kind of system, do you see anything that's troubling for us? Can we run into some trouble? We choose voltage and current as base?
It'd be different on either side of the transformer?
Right, so if I choose voltage and current as base, but then the voltage and current changes when I go through a transformer, right? So that's not very convenient for us. But the thing that's conserved for this entire system is the power, right? Power doesn't change from one side to the other. So to make our life a little bit easier, one thing we should make a choice is we should choose one base power for this. Okay? We should choose one base power because power is conserved. So if my nominal power is 100 MVA on the primary side, then the nominal power for the secondary is also 100 MVA. Right? When you write a transformer, you only have one nominal power. So that tells us we should, for the first choice we should make is take a power base, right? Take a base unit for the power, okay, right? Okay, so that's first choice we should make. Then what we do, then we have another choice to make, right? We need to somehow pick a base unit for either the voltage or the current. And what we do is we choose a voltage base for each voltage level. Okay. So what we want in our per unit system is we want this per unit system to make the transformer go away. So what we do is we'll choose one nominal power base, then we'll choose voltage bases for each side of the transformer. And this turns out will make our life the easiest. Okay, make life easier. Okay, so summarize as again, so the rules, these are the important rules. Okay. Important rules is choose only one base power for the entire system. Okay. Choose one base power for the entire system. This is average choice you can make, arbitrary choice you can make. You should pick a base unit that's somehow related to more related to your transformer, right? So if you're talking about a large system, then most likely it'll be 100 megawatt or 1 gigawatt, not 100 watts. Right? So make a reasonable choice, but this is arbitrary choice. Then what we do is we choose one base unit for each voltage level if you have a transformer. Okay, so you choose the nominal rated voltage according to the transformer ratings. Okay? And the nice thing is if you choose it this way and you do division, turns out everything works out for the transformer. It's as if we don't have a transformer. Okay? So that's a choice we'll make. Okay, and given these choices, basically then we'll determine how do we choose the other units. Okay, how do we choose other units? If our choice to make, if we made the choice of choosing a power and the voltage basis. Okay, so once we know this, then we can do computation. Then our computation works this way. Okay, so this is our idea of choices. So if you look at, so for example, how do we do base current? Well, so if you look at how we do base current, so let's think of what choice we have made, right? S6 VI star. So we choose this base. Okay, we choose this base already. So what we have is the base as per unit. What we want is this equation holding per unit terms. Okay, so you divide by the base unit. Okay. So what we get, you rearrange this. So what we have is we have the base unit for current as the base unit for power divided by voltage. So what this tells us is we have one base current for each voltage zone. Okay. So the power is for the entire system. Then the currents and the voltages are one base unit per zone. Okay, one base unit per zone. And then the same thing as for the base impedance, right? So we have, we have V equals Z times I. So we want V per unit equals Z per unit, I per unit. So if you look at all the choices we make, this is the base should be like this, and you substitute the power into it, we have this kind of equation. Okay, so this is one base unit per zone. Okay, we have one base unit per zone again for each voltage zone. Okay, so the mechanics is you pick VB for each zone, you pick SB for the entire system, and you again going and plugging all those calculations. Okay, then we plug in the calculations. So all of this seems, fairly dry and tedious. So let's take a break now. Let's take a 10-minute break. So we'll again come back at 10:22 and look at some examples of transformers and how to do this calculations. Okay, so we'll come back in 10 minutes. So meanwhile, if you have any question about the homework or the class, you can ask now if you want.
I actually have a quick question.
Yeah, sure, go ahead.
So you said it said that to choose one base power for the entire system. We assume that the system consists of only one transformer. What if there's
no, can have multiple transformers. That's fine.
We can have one base power for multiple transformers.
Yeah, because transformers conserve power, right?
Okay.
So going through a transformer doesn't change power. So power is, in some sense, conserved for the entire system. So it doesn't matter how many transformers you go through, it's the same power that's being transferred. So one base power for the entire system.
So would we choose the transformer that has the greatest nominal power as the base value?
No, because not really, because the base value is normally chosen to be what the nominal load tends to be, right? So if you look at the chain of transformers, some transformer may have a higher rating than the other transformer.
Mm-hmm.
So if you choose the largest one, then every number, you make it a number like 0.2 or something, right? Dividing it. So normally, and we almost never operate a system that close to the power rating anyways. Okay, so what normally we do is we look at nominal load that's supplied by all these transformers and pick some value that close to nominal load.
Okay. Okay. Yeah, sounds good.
Yeah.
Thank you.
Okay, all right, so let's get started. Okay, so now let's look at why we do all this per unit stuff, right? So why bother with per unit? So the nice thing is, let's look at what happens for a transformer. Okay, let's look at. So if you look at this ideal transformer, this is in SI units, right? So I'll here the V, I, okay, are in SI units. Right. So what happens if we look at per unit voltage in transformers? Okay. Let's say I want to look at per unit. Let's see what happens to them. Okay. So what we have is V1 over V2 is N1 over N2. We always have this. Then let's make the following choice, right? So we know for a transformer, the rating for the transformer is such that the nominal voltage is the same as N1 over N2. Okay, the rated voltage is same as N1 over N2. So what do we do is we can choose the base voltage to be the nominal voltages. Okay, so this is take the base voltage to be the rated voltage. And so what happens we choose this to be the rated voltage? Well, so if you let's look at this ratio, okay, what is the per unit ratio of the transformer voltages? It happens, so let's divide. Okay, so per unit by definition means I divide by the base unit. So this is V1 over V2, V2 base over V1 base. This is now N1 over N2, right? Because it's a transformer. But then the base ratio of the secondary to the primary side is N2 over N1. Okay, right? So we flip the numerator and denominator when we do the base unit division. So this comes out to be 1. Okay, so this has V1 base per unit equals to V2. So V1 in per unit terms equal to V2 in per unit terms. Okay. So this in a, I guess, ideal transformer. So let's look at ideal transformer first. The ideal transformer, well, if you talk about per unit voltages, they're equal. That means the transformer is not there in per unit terms. Okay, so if you look at your transformer, if you now do a per unit, this is just a wire. Okay, that's just as if the transformer does not exist. Okay, so that's why, again, why we want to use this kind of per unit. You can divide. Because we use per unit, we normalize by the rated or nominal voltage at each side of the transformer disappears for us. Just because the turns ratio cancel. We do, right? If we look at the voltage at both sides. Okay, so we no longer have to worry about this transformer anymore. Okay, so that's why if you look at any software that does calculations, does power system calculations, always the calculations are done in per unit for voltage. Okay? We almost always talk about the voltage in per unit terms. We never talk about the in SI units. Because the reason is we compute the per unit for 1 for the primary. We know what it is for the secondary. Okay? We know what it is for ideal transformer. Okay? So this is, right? So of course, V2 is not equal to V1. In SI terms, they're not equal, but in per unit terms, they're equal. So that makes life very easy for us, right? We can say for the system, the voltage, the nominal voltage is 1, right? Yeah. We are compute the voltage to be 1, and the voltages are all 1, all close to 1. We don't have to talk about, I have a step up transformer, so it goes from 10 kilovolts to 100 kilovolts. I have a step down transformer that goes to 20 kilovolts, this kind of thing. We do per unit, all this goes away. Okay, some unitless quantity for voltage that we can just talk about. We don't need to think of transformers anymore. Right? That's why if you open up the code for any of the software, the first thing they do is convert everything to per unit system. Then all the equations are in per unit. Okay? And for a lot of times, the code doesn't even bother to give you back SI units anymore. Just spits out the per unit quantities. And as power engineers, you get to be very comfortable in per unit quantities, because you see that most of the time, right? Just makes your life a lot easier. Any questions about this per unit things? About voltage, right? Okay, so per unit numbers in per unit quantities, voltage across an ideal transformer is equal. That's why in the beginner class, I said, per unit is essentially large part invented to make this happen. Because I don't need to talk about transformers. I don't need to have many voltage levels anymore. So similarly, nice thing occurs if you talk about current, right? So as expected, for currents in your transformer, very nice things happens again. Okay, so if you look at the current, let's look at the current ratio in per unit terms. So this is I1 over the base unit I choose for the one side, I2 over the base unit I choose. For the secondary side, okay, so this is I1 over I2 times I2 base, times I2 base, I1 base, okay? So let's choose the base unit, in the reasonable way, right? So how do we choose the base unit? For the primary side, let's choose these as the base for power over the base for voltage. Secondary side, remember it's the same power. The base for unit for the power is always the same over voltage. Okay? So if you divide this two, what we have is I2 base over I1 base. Just making the division, we have V1 base over V2 base as N1 over N2. But I1 over I2 in ideal transformer is N2 over N1. So this tells us I1 per unit, I2 per unit as N2 over N1 times N1 over N2. This is 1. So again, I1 per unit equals to I2 per unit equals to 1. Okay. Sorry, not equals to 1. They're equal to each other. Okay. So again, we use per unit things. For current, also they're the same across ideal transformer. Okay, so no need to talk about different currents in different size, talk about turns ratio anymore. That's taken care of in the per unit system. Okay. Okay. Any questions about the current or the voltage? Okay, so okay, so let's look at now what happens when we have a practical transformer, right? So does all this nice thing still work? If I have, shunts and impedance in series and things like this, right? If that still works, then really we can abstract away the transformers. So let's look at what happens to our per unit for a non-ideal or practical transformer. Okay. So now let's look at, let's say I have something in the, secondary side, XL. Okay, let's say I have some load in the secondary side across the ideal transformer. So what happens when we do a per unit analysis? What happens when we do per unit analysis? So when we first do a per unit analysis, the thing we need to ask is, let's look at which side we're looking at this, okay? So let's say we're looking at this from the primary side. So we're looking at this from the primary side, then x1, looking across ideal transformer, we have seen this before today. This is n1 over n2 squared xl, right? If we look through the primary side, refer this to the primary side. So if we look through this from the secondary side, then of course x2 just xl, right? So you look at from secondary, this inductor is a secondary, so just xl. So if you remember that x1 is n1 over n2 squared xl, so this gives us x1 is n1 over n2 squared x2. Okay? So this is the two equations relating to each other. So now the hope is, in per unit system, this n1 over n2 squared term also disappears. Okay, so what we want is we want x1 per unit equals to x2 per unit. That's what we want, right? If this happens, then it says, if even for a non-ideal transformer, it's okay, right? We can still always throw away the transformer, and again we can pretend as if the transformer was never there. Okay, so that's what we want. Let's check whether this is true or not. Okay, let's check if we can get rid of this n1 over n2 squared term here. So let's try to get rid of this. Okay, so let's look at what happens for per unit impedance. So same thing as x, we can write, so impedance is, for z is n1 over n2, z2. Okay. So then z1 is z1 per unit times z1 base. Okay. This is just expanding z1 and z2 from SI terms into per unit terms. Okay. This is just what we have, right? So remember, we said that once we chosen the voltage and the power base units, we cannot choose the impedance base units arbitrarily. So we must have Z1 base as V1 base squared over the base power. Z2 base is now V2 base squared over power, right? This is what we must have. Okay. So plug this in, Z1 per unit, V1 base squared, power n1 over n2, squared z2 per unit, v2 base squared over power, okay, over the base unit for power. So power cancels, right? Power cancels on this side. So I have z1 per unit as v2 base squared over v1 base squared times n1 over n2 squared times z2 per unit. This is what we have. So of course, this is n2 over n1 squared, right? This is how we choose the voltage. We choose the voltage as the rated voltage of the transformer. So we have z1 per unit equals to z2 per unit, right? So the ratios cancel, the n1 over n2 ratios cancel, and this is what we have, okay? So again, we can get rid of the transformer if we just look at per unit system. Okay, so if you look at the transformer model in per unit systems, the ideal transformer go away, right? Disappears completely and gets replaced by simple impedances. Okay? Gets completely goes away. All we have is simple impedance. Okay? So this is what's nice about it. Okay? A transformer in per unit system Okay? Goes away, and now we have, and we don't need to worry about the transformer anymore. Okay? So this is the basically the crux of the idea of a base unit. Okay? So, and the idea is pretty simple. Just divide by the reasonable quantities that you think you would divide by to get normalization. Okay? This actually took us a while to get to this point. So if you look at the very early calculations, so in the 30s and 40s, look at very early things. Now, per unit system was not quite there yet. So you see long equations, being derived with all these terse ratios in it, people trying to get the equations calculations correct. But then the field realized that it's much easier if you just divide by everything first. Right? Just divide by things first. So then your life becomes much simpler. And when people really starting to write computer programs, when we start writing digital computer programs, then we very quickly realize that we should do things in per unit terms, okay, to get rid of all the transformers. Okay? Any questions with this?
Professor, can you go back to one slide?
Sure.
Thank you. And go back one more slide.
One more slide.
Thank you.
Any questions on this slide?
Thank you.
All right, okay. Right, so the idea is to get rid of the transformer. So real life is not quite that simple. Okay, not quite that simple. It's not quite that simple because when you buy a transformer, okay, the manufacturer transformer really doesn't know, how big your power is, for example. Okay, so for example, so what do you do when you buy a transformer? So when you buy a transformer, what kind of value do they give you? Okay, so when you look at the manufacturer data, you buy a transformer, you get a data sheet. That actually gives you everything in per unit systems. Okay, so if you buy the data sheet, what the transformer will say is, I'm rated at the power rating as 100 MVA, sorry, 10 MVA and 200, sorry, 10 MVA and 20 kV. Okay? And what will give you is all the impedance will give you basically in per unit systems. Okay, so your buy transformer it actually doesn't even bother to give you SI units for all the impedance and the shunt and everything. Okay, what gives you is it gives you things referred to as own base units, own base units. And sometimes the issue is if you look at this generator or the transformer or the whatever manufacturer data you have, as basically everybody picks their own base power. Right? Because I'm making a generator, I think, 10 MVA is a reasonable base unit for my generator. But maybe the next generator in my system has 50 MVA as its base. Right? Maybe the other one has 100 MVA as its base. So to do this, right? So for example, I have generator 1, but maybe generator 2 decides to have some base unit of 20 MVA and 50 kV as base units. Okay, this is very common. You buy the generator doesn't know what you want as a base unit, so it just gives whatever it thinks as reasonable in the data sheet. Right? So now but when we do a system study, right? I have to make sure that things are consistent, right? I can only pick one base power Okay, so if you have two generators or two transformers, they don't take the same base power. I need to make the things consistent to put in the system. Okay, if I'm connecting two generators that has a different base voltage, but they're connected to the same voltage level in my system, then I need to make sure they're all referred to a common voltage. Okay, to a common voltage. Right. So for example, if I have a question. Okay, so I'm gonna mute the mic if there's no question. If I have a question, I'll mute that now. Okay, thanks. So what we have is, for example, I have a bus bar like this, have G1 and G2 connect to it, right? So what they must have, they need to have the same base units, right? For my analysis to make sense. There's no transformer in between, but the data sheet don't. The data sheet doesn't give you the same base unit. So what we do is the data sheet gives us everything in per unit quantity, but then we need to know how to do a change of bases. Basically, we need to know how to do this kind of change of base, right, to make everything make sense. And then finally, we can arrive at a situation when everything's clean and it's a simple circuit and things like this. Okay, so this is what we want. So this is a base conversion, right? So how do I do base convergence? Okay, so, and the idea is the following. Okay, so let's say I have an impedance, and I want to change the base unit that this impedance is normalized by. Okay, I want to make a change, right? So if you look at the actual, so actual means the ISI unit. This is equal to the base of the new things times the base of the per unit refer to the new base. This is equal to the per unit refer to the old base. Okay, so this is always true, right? So the SI unit, the SI value or the actual value of the impedance is related by the per unit times the base quantity. Okay, so if I want to use a new base for this is per unit, the old base divided by the old base over the new base, right? So this is just straightforward division over. But then we're not quite done yet. Okay? Because remember, we never give stuff with the base units are never given for impedance, they're given in terms of power and voltage. So I need to convert this to power and voltage values. Okay? So for whatever base we have, we always have this relationship. So continuing on with this equation, we have the O per unit system old divided by VB old VB new squared. Okay, so this is our new. This is how do we convert impedance from one base to another base. Anyway, this is what we have. Any questions with this calculation? Right. So again, in practice, what you get is you got data sheet saying that this is whatever the transformer of the generator. This is what the power and voltage base for that piece of equipment is. So we need to do a base conversion because at most we can pick one power in the whole system, right, in the entire system. So this is one equation we use, right? So it's not complicated. You just have to know where to find this equation. Right? You asked you a question on this. And one nice thing that happens for us is often the voltage will be in a So often what happens for the voltage will be in a similar, will be in the same value. Okay? Because what we have is if we have two generators, G1 and G2, if they're connected to a terminal, they will always, almost always have the same base voltage. Right? They always have the same terminal voltage. Okay? So 99% of the time, the base voltage for the base unit for the voltage is the same. So what we have is we have the new per unit as the old per unit SB new, SB old. Okay? This is what we almost normally 99% what we will have. All right. Okay, so let's do an example, right? So after seeing all the sort of formulas, let's do an example. Okay, so let's say I have some generator, and the generator is rated at 10 MVA, 20 kilovolts, and I have some synchronous reactance as 0.9 per unit. And but I connect this to a larger system, and the larger system has a base of power that's 10 MVA, that's 100 MVA, right? Right. Again, remember, this was discussed in the break that for the large system, we normally pick a base unit that's similar to the load we have in the system. Okay, so this may be larger than the generator, what the rated unit for the generator is, right? Because we may have more than one generator in the system. Okay? So this is fairly often we'll see this. Then what we have is the, right? So this is a simple formula. We apply the new synchronous reactance is the old synchronous reactance times the ratio of the power. So this is of the base power. This is 0.9 times 100 MVA over 10 MVA. This is 9 per unit. Okay? 9 per unit. Questions with this thing? Okay, so this is not super exciting calculations, but we do this. This is sort of necessary. We do this very often when we work with large systems. So let's look at a slightly more exciting example. So let's look at an example where I have two transformers, a generator, a transmission line, and a load. Okay, this is more exciting and example. Okay, so what is the information we get, right? So the goal is to convert this to a circuit. Okay, so the goal is to, so the objective of this is to convert to a circuit. Which means I don't want to see the transformers, right? I want everything to be in per unit system, so I can do calculations easier. Okay, I don't want to refer things back and forth. I want to do one. I want to convert this to a single circuit. And these are pretty common sort of data you see, right? What you see as a generator will give you this sort of data. Okay, it's base power, terminal voltage, and the synchronous reactance in per unit terms. Transformer will give you the base power, the rated voltage on each side, and the synchronous reactance for the transformer. Okay. This is also the step down transformer will be given this way, and we have a load. All right. So, and the transmission line, this is in SI units. Okay, for the transmission line. Because the transmission line just in, is for each kilometer, you have some resistance. So this is in ohms per kilometer. Okay? So we want to convert everything to a circuit that we can understand, okay, that we can do calculations with. Any question about the setup of this problem? Again, this is a pretty typical problem you'll see in the homework and in the exam. Okay, pretty typical. Okay, so let's look at what step we have to use. Okay, so the first step is to choose a base power unit for the entire system, right? So this is what we have, we can choose the same unit for everything. So we need to choose a base power unit for the entire system. And when we make this choice, so we should choose some number that's, that's reasonable for us. So a number we'll pick here is 100 MVA. I'll just pick this 100 MVA. You don't have to pick this. You can pick 50 if you want. You can pick 10 if you want. But a normal number we like to pick is 100. That's a nice round number. You'll see. Yeah, so it's a number we can pick. And in homework exams, you'll normally be given this. And the reason you'll be given this is I don't want to create, so it makes grading harder if you each are allowed to pick your own. Okay, so in your homework exams, you'll be told 100 MVA is a base. Please use that. Okay, don't go and say, oh, I don't like the number. I'm going to assume another base unit. I'm going to redo the calculation list. Okay, you'll make the TA very angry if you make that choice in your homework. Okay, so use the base units you're given to make grading and homework solutions everything much easier for us. Okay, so yeah, just one thing to be in mind of. So let's choose the base voltage, right? So again, this is 100 MVA we have chosen. Now we need to choose a base voltage. Right? And the idea to base voltage is we can have one at each level, right? We can have one at each level. Okay, so there are 3 levels of voltage, okay? There are 3 levels of voltage here. So one for the generator side, one for the transmission line side, and one for the load side. Okay, there are 3 levels. And normally what we just choose as the nominal voltage at each side. Okay, so for example, here we'll pick the base to be 11 kV. Here we choose a base to be the 132 kV. Here we choose a base to be 33 kV. Okay. This makes your life easier, right? So if you look at the data sheet, as G1 is given to be 11 kV, the line transmission line is 132, and the load is 33. Okay, so choose these for the base voltages. Okay, so make our life a little bit easier. All right, any questions about the power and the voltage choices? Okay, so once we choose these, now we need to do the conversion, right? We need to convert G1 to the basis that we have, convert the transmission line to the basis we have, and convert the load to the basis we chose. Okay, so not very difficult, but just division basically, okay? Loudest division. Right, so remember that G1 is rated at 75 MVA. So the old basis is 75 MVA. Okay. The new base we chose is 100 MVA. So XG is given for the old basis, okay, for the 75 MVA. So we need to do a conversion, right? So the new synchronous reactance for us is the old synchronous reactance multiplied by the formula we derived, new as the old, the 1.83 times 100 MVA divided by 75 MVA Then you do this division, we got this is 2.44 per unit. Okay, and this is in the new basis that we have. Questions with this conversion?
Professor.
Yeah, go ahead.
So the S base new that is 100 MVA. Is it from the problem?
Yes, it's not from the data sheet of the generator. It's from the choice we made, right? So remember, so the first step is we need to choose a base MVA for the entire system, and we pick 100 MVA for the as a new base. So this is normally an arbitrary choice we can make. So when you do a homework and exam, you'll be told in the problem statement, the new base or the base for the base power for the system is 100 MVA. You'll see a statement like this.
Okay, thank you.
Okay, yeah, you'll see a statement like this. So no, so if you don't know how to choose, we'll make the choice for you. If you work in this field and you're an engineer, you'll be choosing this on your own. And a surprising amount of time is chosen for the basis for this base. Like your manager will probably have a different number than you, and you guys spend a lot of time choosing this number. Okay, so, and sometimes the software will choose one for you. So in your homework, I will choose one for you. In this time, I chose it to be 100 MVA. The rest is no more choices, right? It's, we need to do calculation. So this is the converting generator one. Any other questions on this?
Hi, Professor.
Yeah,
so why is like the XO equal to the XO times the S space new over S space old? Can go back to the slides talking about that.
Oh, okay. So we derive this equation. Oh, hey, this actually online makes this thing easier. We're teaching on the board. I'll have you raise it long time ago. Okay. So yeah.
Yeah.
So this is the equation we had, right? So
yes. But which one, like the Y is way old over the VB old over the VB new?
Oh, okay. What happened to that? Okay, yeah, good.
Yes.
Good question. So what happened is this is normally the case, right? This is normally the case. They're equal. So why are they equal? So let's look at this problem. Why are they equal, right? So if you look at this, right? So the generator, sorry, not S, this is a V. Okay. So this is VB old, right? For the generator case. We talk about for generator one, then this is the VB new for generator one. Okay? Because the generator is having a voltage that's basis of 11 kV. The transformer for the primary side or the side connected to the generator has a base that's that's a new voltage base, but that's also 11 kV, right? So what we do is, okay, so what we do is when we choose the base voltage, we'll choose it to be 11 kV as well. Okay, we'll choose it to be 11 kV. So what we have is VB new is 11 kV. VB old is 11 kV for the generator. And VB old is also 11 kV for the transformer.
Oh, yes.
Right, so we choose 11 kV such that all these numbers are the same. Yeah. Right, in this case, because the base voltage is the same, so we don't have this bracket, right? Because this is 1 inside the bracket.
Yeah.
Okay, it's a good question. Good question. Yeah. So that's vast majority of the time, the voltage will be connected to the terminal voltage, right? So the voltage will not differ. Right? We may give you a question where the voltage differs, but most of the time, the voltage is fairly nice to work with. Okay. All right. Okay. So this is any more questions on this case?
No.
Yeah, so if you have questions, please ask. You'll be seeing, 5 questions like this on your next homework. Okay, so homework will be posted tonight, and you be all like this, basically. You do a lot of conversions. So, okay, so let's look at T1. Let's look at T1. Okay, so we convert G1 already. Now let's look at T1 with this transformer. So what happens in the transformer? Well, we have a in series impedance, right? T1 on this basis. So let's convert this to the new thing. So this again, what we have is xt1 new. Same calculation we did, SB new, SB old. So again, remember the voltage is the same from the new to the old. So what we have is 0.125 times 100 over 75. This is 0.166 per unit. All right, so this is what we have for T1. Now let's look at T2. Okay, let's look at this transformer. We'll do the transmission line next, but let's do this transformer. Okay, so this is rated 45 MVA with XT2 of 0.125. New. The old, same equation as before, 0.125, 100 over 45 now, and this is 0.278 per unit. Okay, so same calculation as before, just converting all the impedance to the new base units. So let's look at L1. Okay, let's look at L1. Okay, so remember this is a 20-kilometer long line. So to get the impedance in SI units in ohms, what we have is 0.18 plus J 0.4 times 20, right? So this gives us the total impedance on the line. Okay, so again, fairly easy calculation. Then I need to convert this to the base units. So the equation we use is VB squared over SB. So remember, for this part, the base we chose is 132 kV. So this is 132 kV squared over 100 MVA. Divide things out, we get, sorry, this is the base. So the base is 174.2 ohms. So the L1 per unit, L1 over the base unit, and this is 0.021, 0.46 per unit. Okay. All right, so this is the calculation we do for the line impedance. Right? And this is again a nice result because if you look at the per unit, right? So if you look at the absolute ohms, as 3.6 plus J8. Is it small or large? It's a little bit more than 1, but as ohms is a lot smaller than all the other units we have in the system. So is it small or large? We don't know. But once you convert to a per unit system, it looks fairly small, right? Looks fairly, the impedance on the transmission line is not very large. So again, per unit gives us a good basis of comparing things with. So at the end, last step, we need to convert the load to per unit. So load, what we have is MVA. So what we have is, so P plus JQ is 10 times So let's do the P part first. Okay, so it's 0.8 power factor lagging. So P is 10 times 0.8. This is 8 megawatts. Q is square root of 10 squared minus a squared. This is 6 megavar. So if you do the per unit conversion, then we have P plus JQ per unit. This is 8 plus J6 divided by 100. So we have 0.8 plus J0.06 per unit. Okay, so these are the per unit terms. So at the end of the day, what we have is we have this very nice circuit. Okay, basically it's just some voltage connect to an impedance and another inductive impedance, connect to a transmission line, connect to another impedance, connect to a load that's 0.8 plus J0.06. So this is J0.278. Okay, so this circuit is now a very simple circuit. Okay, so we want to find the current, we can. It's very easy. We want to find the equivalent impedance, we can. It's also very easy, right? So this has basically help us to convert a very complicated system to a much simpler system. Any questions with this chain of conversion? Okay, so when you use computer, when you use software, the software will do this kind of conversion for you, right? But when we do, for homeworks and for exams, you should show the steps. Okay, you should show the steps. So if you want to write your own program to do the calculations for you, you're welcome to. But at least when you write down the solution, you need to show the steps. Okay, you should show the steps. Right, so let's finish today by looking at one example. Okay, so this example is the following. Let me write down all the problem things. It says, I have a transformer, a single phase transformer that's rated at 20 kVA for 120 volts. Okay, so now this question is a little bit tricky. It says the equivalent impedance referred to the secondary as the equivalent referred to the secondary as 0.0525 angle 78.13 degrees ohms. Okay, so I'm going to refer this to a secondary, and we have this value. Okay, and this now we have as now says use the transformer ratings as base units. Find the equivalent impedances refer to the primary and the secondary. Okay, basically it says, let's do a Let's convert this from SI units, from ohms to a per unit system. And let's find the per unit system to either side of the transformer. Okay, let's do this calculation. So in this, again, we're told what the base units are. We're told S base is 20 kVA. Not 20. kVA. We're told the V base 1 is 480 volts. V base 2 is 120 volts. Okay. So we want to convert everything to per unit, right? Convert everything to per unit. So let's first convert the equivalent circuit as the second. So let's do this. Let's look at the secondary side per unit. Let's do this calculation. Well, this is given by the base at the secondary side squared divided by the power on this side. Okay. This is the So let's first find the base for the secondary side. So you plug this in, squared over 20 kVA. This gives us 0.72 ohms. Okay. So now our secondary side per unit is just 0.0525, angle 78.13, divided by the space unit I have, which gives us 0.0729, angle 78.13 unit degree per unit, right? So we don't normalize the angle, we normalize the magnitude, we got this number. Okay, so this is in the secondary side, the secondary per unit is 0.0729, angle 78.13 degrees. What is the, in the primary side? What is the what per unit? So if I refer everything now to the primary side, inside the secondary side, what do I get? Right, so remember the answer is easy. The same, right? So our the whole point is to, or one, not to worry about which side of transformer we're referring to. So will turn out will be the same. Will be the same. This is just how per unit system works. And so if you want to do the check, you can do this check. Okay, we want to do this, we could have done this, right? So to do a sanity check, we can do is, let's do this in the not base terms, the normal terms. So what we have is N1 over N2. Let's reflect this from the secondary to the primary side. So what we get is 480 over 120 squared times the 2. This is 0.84 angle 78.13 degrees ohms. We can look at the base for the primary side. So this is the voltage at the primary side divided by the power we picked. So this is 480 squared over 20 kVA. We got 11.52 ohms. So if you want, we can do the division. Z1 per unit is Z1 divided by Z1 base. You get the same answer as before. Angle degrees. Okay, the exact same number as before. So that's a sanity check, right? So if when you do a problem that's in per unit base, in per unit quantity, give me the transformer secondary impedance as the primary impedance, they're the same. Right? They are. That's the way. That's why we pick the base unit this way. Okay. All right. So we'll end the lecture here today. Okay, so as a reminder, homework due tonight, midnight. 11:59 p.m. So the TA, she has an office hour. So if you have questions, feel free to ask her in the office hour. If additional questions, maybe you can't make it to the office hour, you can email me. I'll try to answer before tonight. Right. So if no more questions, see you on next Monday. So the new homework will be posted tonight. The second homework will be posted tonight. All right. Thanks, guys.
Thank you, Professor.
Hi, Professor.
Yeah.
Can go back to example 3.2.
Yeah, sure. Go ahead.
Example 3.2, please.
Example 3.3. Is this not example 3.3?
3.2. The
Oh,
second
3.2.
question. Yes.
Are you talking about the book or the thing we covered in class?
Oh no, it's just a thing covering class. It's 3.2.
Okay, so